So hello dear friends, I'm back with the problem number 3 and 4 from the SFD and BMD. So in this question we will be solving an overhanging beam and a beam with point moment. So let us have a discussion on that. So kindly look at the question. So in this question we have a overhanging section which its length is about 4 meters. And we have a UDL of 20 kilonewton per meter. So the first step, obviously you all know, is the calculation of reactions. It's easy, you solve it. And now we are going to find the shear force at different locations. Okay, so I'm going to represent this entire system here as a free body diagram. Upon calculating the moments and by applying the equilibrium equations, we found that the reaction RA is equal to 20 kilonewton. This is equal to 70 kilo. So first analyze the question and then we will go with the solution. So upon analyzing, we can say many things about this solution. The first thing is that we can expect a step-like variation at the location B, at B and at A. There will be an inclined straight line representing the points C and D. This much conclusion can be made from the basic free body diagram itself. Now let us find the values. So what is the value of shear force at D? The value of shear force at D is equal to 10 kilonewton and the value is going to be positive because if you consider a section right here, the force is on the right hand side in the downward direction, that is going to be positive. So now let us write the shear force between B and D. I am not considering the reaction at D because to get a step-like variation, I should take two shear forces, one without considering the point load at that location and second by considering the. So between B and D, I have the value 10 kilo. So the shear force at B is going to be the 10 kilonewton minus 70 and the value is going to be minus 60 kilonewton. A sudden change has been observed. So when you start to travel from the point B towards C, you can see that the value is gradually increasing from this minus 60. So we can say that when you reach the point C, the shear force is equal to plus 10 minus 70 plus 20 into the distance is 4. So the answer is going to be minus 60 plus 8. So the value is 20 kilonewton. See the change that has happened here. Right? So when you move across AC, again you will be having only the 20 kilonewton, and when you reach the point A, the value is equal to 20 kilonewton. So this has to match because when you start from your left hand side and when you reach the point A, the value of shear force will be equal to your reaction. For all the questions that will be the same. So if you get some different answer, that means there's some kind of mistakes has been committed by you during the solution. Okay, so kindly cross check. So this is the shear force value. So let us plot this value. So the value at B is how much? It's going to be positive 10. So let us mark this as 10. Up to the point B, the value remains same again 10. When it reaches the value at B, it has suddenly changed to minus 60. This is minus 60. Again, when you reach the point C, the value booted to positive 20. So it has reached. So we have a positive 20 here. So the value is going to be 20. And again here, the value remains same 20. So if you join here, there is a vertical line, vertical step-like variation, horizontal line, again a step-like variation, again an inclined line variation, and a step-like variation. So the value is going to be positive here, it is positive here, it is negative here, and again positive. So what we can conclude? We can conclude that at this particular location, shear force has become 0, and therefore we can expect a maximum bending moment to happen at that location. So in order to find out this, I'm going to consider this length as x. Now the question is, what is the shear force at x? Obviously the value should be 0. So let us solve this. So if you consider your right hand side, you can say that 10 is positive minus 70 negative plus 20 into x. This should be equal to how much? 0. So upon solving, you can say that 20x is equal to 60. X should be equal to 3 meters. That means this distance will be 3 meter and this is going to be 1 meter. Right? So we have to consider the moment at that particular location 1 and 3. And at this location, you can expect a maximum moment. So now let us draw the, no, not to draw, let us calculate the bending moment. You can say that bending moment at A equal to 0. Now, what is the bending moment at D? Bending moment at D is 0, free end. There is no load beyond C to create a moment out there. So the bending moment at B equal to 10 into the distance is 4, sign is going to be negative because this is going to create a sagging effect, hogging effect. So the value is minus 40 kilonewton meter. Now the bending moment at C is equal to minus 10 into 4 plus 4, 8 plus 70 is going to create a sagging effect. So 70 into 4. Now we have to consider the UDL. So that is going to create a hogging effect. So minus 20 into 4 will fetch you the total load into the perpendicular distance is 4 by 2. So this is going to be minus 80 plus 28 to 280 minus 160. So this is going to be how much? 200 minus 160, that is equal to 40 kilonewton. Okay, now we know the moment at A is 0. Now the last one we are supposed to calculate the bending moment at the x, where you will get the maximum. So this is 3. So if you take the moment at x, the value is going to be minus 10 into 3 plus 4. So 10 into 4 plus 70 into 3 minus 20 into 3 into 3 by 2. This is how the equation will come. So let us see what's the answer. 80 kilonewton. This is how you have to. Now let us plot the bending moment. So we have to take an intermediate position to draw all these things. So at this point the bending moment was 0. When we reach the point B, the value is nothing but minus 40. So it's 2 and 3. So it became plus 40. At the point A, the value is equal to 0. No. Now if you connect these 2 points, it will be by a horizontal straight. These 2 points will also be connected by a horizontal straight. Now the question is, how will you connect between plus 40 and minus 40? It has to be a parabola. Now the question is, what will be the peak of the parabola? Right? So the peak will be obviously somewhere at this location and the value is going to be 80. So it will be something like this. So from here you can have a peak like this and slowly it will come to the, this is how you have to do. The value is 80. So kindly cross check whether you are getting the same value or not, or whether there is a mistake in my calculation. Anyway, the procedure has to be like this. So we obtain the maximum bending moment and the equations. So this is how you have to solve the problem of overhanging beams. And if you look, one peculiar thing here, look here the sign of the bending moment was negative, here the sign was positive. The bending moment has changed its sign from negative to positive. And what is this point called? This is nothing but the point of contrafluctuation. Sorry, the location of point of contrafluctuation. So at the location of x, so say this point is y. Let us say this way. At bending moment at y should be equal to 0. So I'm going to take, so it is somewhere here, located somewhere here. I'm going to keep this distance as y. So upon solving, I can say that 10 into y. It is going to be negative plus 70 into y minus 4, because this distance is 4. So this has to be y minus 4. Again, negative 20 into y minus 4 into y minus 4 by 2. We solve this, we will get the value of y. This is one way, because I have defined the length from here to here as y. See, if you, there is another methodology, not methodology, I will change the y. Let us say this is equal to y. Previously I have taken this as y. Now I have taken this as y. So how will be the, or what will be the equation? So sorry. So this is, so 10 into y plus 4 plus 70 into y minus 20 into y into y. This will be equal to 0. So solve this and get the value of y. That's for your, consider it as a homework. Okay, you solve this and get the value of y. So this is how we have to calculate point of contrafluctuation and point of inflection. Right. Now let us see the last problem that I am going to discuss under the shear force and bending moment diagram. Here you can see some peculiarities. I'm not going to solve this, I will explain this. See, this is also an overhanging beam. So when you have an overhanging beam, definitely you can expect a point of contrafluctuation. Okay. The speciality, when we compare this question with the previous question, the only speciality is that we have a point moment like this. I hope you all can see. If you didn't see, I will circle it out. See, kindly look here. You have a point moment. So you may get confused how to solve these things. See, in order to calculate the reactions at A and reactions at B, okay. So when you calculate the reactions, do not add this moment in the Fx equation, because this is a force equation, this is a moment. But when you take the moment equal to 0, you add this 20. There you can use the conventional sign convention. It can be clockwise positive, counterclockwise positive. Anyway, whatever you are familiar with, you go with. Now, when you come, or when you take the case, when you take the bending, sorry, shear force also, this particular 20 kilonewton doesn't have any effect. Because if you look here, the value is 0 here, 0. So when you go towards D, the load is gradually going to increase. Okay, the value is going to be 15 kilonewton, right? So it has reached 50 kilonewton here, 15 kilonewton. So suddenly this point load, this reaction came into picture. So you can expect a step-like variation. So when you include this 32.167, the load is going to change from plus 15 minus 32.167. It is going to get the value of minus 17.167 kilonewton. So between the section CD, this one is going to be same. And at C, you can again expect a step-like variation. So this 8 kilonewton will add to this minus 17.161. You will get it as 9.167 with a negative sign. Again, at this location, you add 8, and finally you got this minus 1.167. So you might be wondering about this negative value. See, there is no need to conclude that always the reaction has to be positive. No. So you just solve the equilibrium equation. Whatever might be, or what value you got, after that particular solution, you use that. It can be both positive, it can be both negative, it can be one positive, one negative. So in this question, when I solved, the RD was in the upward direction and the value of RA it is in negative. That means the direction I am supposed to change. Usually at the support we give a reaction like this. This is the initial sign convention or direction that we apply. If this sign convention is correct, if the direction is correct, then I will get a positive solution. If I get a negative solution, means the sign I have, the direction I have used is not correct. I have to alter the direction. It's done here. When I calculated the value of RA, the sign was minus 1.167. So I concluded that direction I adopted to solve this is not right. So I change the direction downwards. Okay. So this is how the shear force diagram will look like. Now let us go to the bending moment diagram. Okay. So the value of bending moment at this location is going to be 0. So when it reaches here at the location D, the value will be 15 into 1 into 1 by 2. So the value is going to be 0.75. And I need to make a small correction here. This has to be drawn like an invert parabola. Here it is drawn like this. So this is minus 7.5 and this is 0. So in the negative side, when you draw a parabola, it has to be something like this. It is purely related to the slopes that we discussed about the bending moments and the shear force. So in order to have a same slope, it should be like this. Okay. So it reached minus 7. Now if you take the moment at C, it booted to 9.667. When you take the moment at the point B, it becomes 16.514. See, at this location say E, this is location E. Here you have to be very cautious, because when I consider the bending moment at E, I will take two values. Why? See, I have already told you that when you have a point moment, your bending moment diagram will have a step-like variation. So you have a point moment here. So in order to obtain a step-like variation, you should take two bending moments at that location. One without considering that effect, that 20 kilonewton, and one by considering. So let us have two values. So what is the value? So bending moment at E is equal to how much? 15 into 1 into total distance is, from here if you take 0.75, 1.75 plus 0.5. 0.75 plus 1 plus 0.5. Now that is going to create a negative sagging effect again, plus 32.167 into 1.75. Again 8 is going to create a hogging effect, so 8 into 0.75, right? This is one moment. And if you calculate this, you will get it as 16.541. Now, if you take the moment E at E by considering 20 kilonewton, then along with this 15 into 1 into 0.75 plus 1 plus 0.5 plus 32.167 into 1.75 minus 8 into 0.75, you have to consider how to consider this moment also. So now the question is, what should be the sign we have to keep, whether clockwise or counterclockwise, or positive or negative. See, this is a clockwise moment, but we cannot give a sign plus for this. Why? Because the sign convention for drawing the BMD moment diagram is completely different. There we have to consider the effect. So what is the effect this particular 20 kilonewton is going to create here? It's very simple. See, this 20 kilonewton, if you rotate it like this, it is going to bend like this. This is a hogging effect, so it has to be negative 20. So upon adding, it will, see, plus 16.571 minus 20, it is going to be something minus 3.54459, and obviously the moment at the point A has to be equal to 0. It has to be a horizontal straight line. Okay, no, not an inclined straight line. So this is how you have to solve it. So kindly practice these questions, and we will meet with some interesting topic in the next class. Thank you. Bye bye.